Okay, so let's try and unpack this. Imagine looking at like a newborn photo, but not of a person, right? An
Yeah.
entire solar system. And you catch it at the exact moment its first building blocks start. Well, solidifying.
Yeah, it's pretty wild.
That's basically what astronomers have just done. For the very first time, outside our own cosmic backyard, they've actually witnessed the absolute beginning of a new planetary system forming.
Mm-hmm.
So today we're doing a deep dive into this really groundbreaking press release from the European Southern Observatory, ESO. They detail this incredible observation.
Yeah.
And our mission really is to understand how planets actually start, how they're born, and what this amazing discovery tells us about the earliest days of our home, our solar system.
And what's fascinating here, I think, is that, well, we've seen young planetary systems before, plenty of them actually, in different stages.
Sure, yeah.
But this find, it zooms right in on the absolute earliest moment. Like the instant solid stuff starts forming from gas and dust.
So not just a young system, but the very first step.
Exactly. The very first construction phase. It's kind of like finally getting that super early baby picture of our own cosmic family. It gives us this direct window into how it all kicked off.
That's a great way to think about it, a baby picture. Okay, so what exactly did they manage to pinpoint here for the first time?
They nailed down the precise moment that planet formation started around a star that isn't our sun.
Right.
And we're not talking about seeing, a fully formed planet or even a big protoplanet.
No, this is earlier.
Much earlier. It's the actual creation of the first tiny specks of planet-forming material. These little bits of hot minerals just beginning to solidify out of the gas.
Wow. Okay. And where is this happening?
This is all going down around a baby star, a protostar, called HOPS 315. It's about 1,300 light years away.
1,300 light years.
Not exactly next door.
No. And what makes HOPS 315 really, really important is that it's seen as this remarkable analog, like a stand-in for our own sun when it was just forming.
A young version of our sun, precisely.
Mm.
And that analog idea is just so powerful. I mean, we've known for ages about protoplanetary disks, right? These big swirling clouds of gas and dust around young stars where planets get made.
The nurseries, yeah.
The nurseries. We've even seen disks before that have, big newborn Jupiter-like planets already in them.
Right. We've seen those later stages.
Exactly. But this is different. Like the lead author, Melissa McClure, she put it perfectly. For the first time, we have identified the earliest moment when planet formation is initiated around a star other than our sun.
That pushes the timeline way back.
Way back.
Mm.
It really is like what the co-author Meryl Van Hoff said. It's like seeing a system that looks like what our solar system looked like when it was just beginning to form.
So it connects directly back to us, to our origins. You're seeing the process live, basically.
For a process we could only really guess about before, based on leftovers in our own system.
Okay, let's zero in on that then. What are these first specks actually made of? You mentioned hot minerals.
Yeah, so the key thing they detected are these crystalline minerals. And specifically, they contain silicon monoxide, SiO.
Silicon monoxide. Okay, yeah. Why is that significant?
Well, these particular minerals, they only turn solid at really, really high temperatures, the kind you only find very close to the baby star in these super young disks.
Ah, okay. So location matters.
Absolutely. And then over time, these tiny solids that have just condensed out, they start sticking together, clumping up. They're basically sowing the seeds for planet formation. They get bigger, gain mass.
And this is the path towards planets.
It's the very first step. Think about our solar system, the first sort of kilometer-sized building blocks, the planetesimals that eventually grew into Earth or Jupiter's core.
Yeah.
They formed right after this kind of mineral condensation happened.
Right after.
And the breakthrough at HOPS 315 is that they actually caught these hot minerals just beginning to condense.
They saw it in action.
Yes. They found that the silicon monoxide, the SiO, it's there both as a gas and locked up inside these solid crystalline minerals.
Ah, so you see both states at once.
Exactly. Which clearly shows it's literally just starting the process of solidifying. It hasn't all turned solid yet.
Wow.
And like co-author Edwin Bergen said, this process has never been seen before in a protoplanetary disk or anywhere outside our solar system. It's like witnessing cosmic birth, the very first solids forming.
That is incredible. But
yeah,
1,300 light years away, seeing these tiny, tiny specks starting to form. How on earth do they actually see that? That sounds almost impossible.
Yeah, it takes some serious cosmic detective work.
Yeah.
And, well, some incredibly powerful tools.
I bet.
It really came down to combining the power of two world-leading observatories, First up was the James Webb Space Telescope, JWST, the big one.
Right, Webb. Huge deal.
Huge deal. It's a joint project, U.S., Europe, Canada.
Yeah.
Webb was the one that first picked up the chemical fingerprints, the signatures of these specific minerals.
Okay, so Webb found the what?
Kind of, yeah. It found the chemical evidence, but the question was, where exactly in this big disk were these signals coming from? They needed precision.
Location, location, location.
Exactly. And that's where LMA came in, the Atacama Large Millimeter-Sub-Millimeter Array.
Ah, LMA down in Chile. Right.
Yep, operated by ES and international partners in the Atacama Desert. LMA has this amazing ability to map things out spatially. So the team used LMA to basically pinpoint where those Webb signals were originating.
So they work together.
Perfectly. Like ESO astronomer Elizabeth Humphreys pointed out, this whole result really highlights the combined strength of JWST and LMA for exploring protoplanetary disks. They're just an amazing pairing.
And where did LMA find these signals coming from?
Get this. They trace them to a really small region within HLPS 315's disk, a region that's roughly equivalent in distance to the orbit of the asteroid belt in our own solar system.
No way. The asteroid belt.
Yeah, which is just, wow. As another co-author, Logan Francis, put it, we're really seeing these minerals at the same location in this extra solar system as where we see them in asteroids in the solar system.
So it's not just the what, but the where that matches our early solar system.
It's an incredible match. It's like seeing our own past playing out, mirrored in this other system, a real cosmic echo.
Okay, this is huge. So let's pull back a bit. What does this all really mean for us? For understanding our own place in the universe.
That's profound, really.
It feels profound. This isn't just some obscure detail. HOPS 315 is giving us this unique window, like a living laboratory for looking at our own past.
That's a good way to put it. A living lab.
This star, it's like a cosmic mirror reflecting our own solar system's infancy. Remember Merrill Van Hoff saying it's one of the best that we know to actually probe some of the processes that happened in our solar system. So by looking closely at this baby sun, astronomers can now directly test theories about how our solar system started instead of just relying on, clues left behind in old meteorites.
Exactly. It moves from inference to direct observation, which is massive for the field. This discovery, it really gives astronomers a whole new avenue. They can use HLPS 315 as a direct case study for what newborn solar systems look like, maybe across the whole galaxy.
Like a template?
Sort of, yeah.
Yeah.
A really valuable one. So this deep dive into HLPS 315, it's not just about understanding our own past, although that's huge. It helps us get a grip on the universal processes of how planets are born everywhere.
Right. Unlocking secrets way beyond just us. Are we common? Are we unique? This helps answer that.
It gets us closer to answering those really big questions. It lets us ask not just how did our planets form, but, how do any planets form? What are the fundamental rules?
Wow. Okay, so from these tiny, there's specks of hot mineral dust seen across 1,300 light years, to witnessing the actual dawn of planets and the tech that lets us see it. It really does make you look up at the sky differently, doesn't it? Makes you picture our own Earth starting out like that.
It absolutely does. And when you think of these really quick high-temperature events happening way out there around HLPS 315.
Fleeting moments, really.
Fleeting moments in cosmic time, yeah. But they are the exact same fundamental steps that eventually, over millions of years, led to the stable, complex, diverse solar system that you call home. It's quite something.
It really is.
So here's a thought to leave you with. If these tiny hot mineral grains condensing out right near the star are the absolute first solid seeds of future worlds, what does that tell us about the most basic, most essential ingredients you need for any planet anywhere in this enormous cosmos to even begin to form?